The next thing that we're going to talk about is acids and bases. And the Bronsted-Lowry definition of an acid is a substance that donates a hydrogen. And then a Bronsted base then is a substance that accepts the hydrogen or proton. So we can call that H plus or a proton or a hydrogen. Some of the characteristics of a base are that it is negatively charged or partially negative. So negative or partial negative, and that's going to accept the proton. And Bronsted acids usually are the proton donor. So in an example here, we have HCl, which is acting as an acid. That's going to donate a proton to water, which is acting as our base. Our base is going to go fishing for a proton, and those electrons between that H and Cl bond are going to go onto the chlorine, giving it an extra lone pair, making it negatively charged. And now Cl minus is our conjugate base. And H3O plus, or the hydronium, is our conjugate acid. HCl is our acid because it is a proton donor. It's donating its H to the base, which was water. Water is the base because it accepted the proton. In the reverse direction, Cl minus is now the conjugate base because that one is accepting the proton from the conjugate acid H3O plus. So in order to determine if something is an acid or a base, sometimes it's easier to figure out what the base is. And here we have an OH minus that's negatively charged, so this is our base. So then by default, this is our acid. The acid is going to donate that proton to the base. So our base is going to go fishing for this proton. So now when I draw my acid, I have an O negative because that oxygen lost that hydrogen. Those electrons are now on the oxygen. And then here's the O, and it's picked up an H to become water. And in the reverse direction, I have a negative here. This is now my conjugate base. This is the conjugate acid. In the example below here, water plus ammonia, either of these could act theoretically as an acid or a base, but nitrogen is a little bit more likely to pick up a proton. So this is going to grab a hydrogen here from the water, which is acting as the acid. This is the base. So this will become O negative, and the ammonia becomes a protonated conjugate acid. And in the reverse direction, OH minus is serving as the conjugate base. When we talk about acids and bases, we also have to think about the strength of an acid or a strength of a base. So the pKa is the measure of how strong an acid is. And the pKa equals the negative log of Ka. A smaller value of pKa means that we have a stronger acid. So there's a difference there between the products and reactants if we think about the equation. For the pKa of water, this is equal to 15.74, which is not a very large number, which is fine because we use water every single day. We don't want it to be a strong acid and take our skin off. 15.74 is the pKa of water, and that comes from this equation here where we have H3O plus, A minus, so it's products over reactants. We're just missing some charges here. And that comes from these two numbers, the 1.0 times 10 to the 7th times the same number, over 55.4, which is the molarity of water, and that gets to this value, and when you take the negative log of that, we end up with 15.74. The acidity constant, Ka, for the reaction of an acid measures the strength of the acid. So small numbers mean stronger acid, large numbers mean a weaker acid. And we can see that in our table here. The pKa of ethanol is 16, whereas something like HCl is negative 7. So HCl is very willing to donate a proton. Or H+, whereas ethanol is not as willing. The base strength is the opposite trend of an acid. If HCl is a strong acid, the conjugate base, which is Cl minus, when it gives up a proton, is a very weak base. So that is an opposite trend. And that is based on how well the negative charge can stabilize itself. So if it's better at stabilizing, then it's a weaker base because it can stabilize. So if we're looking to rank the following substances in order of increasing acidity, so let's say this 4 is most acidic, 1 is least. We can look at the pKa values on the last slide, and for the pKa of acetone, this is 19.3. For pentane dione, this is around 9. And that's this proton right here we're looking at. For acetone, it was one of these, and for the pentane dione, it's the one in the middle there. For phenol, it's around 9.9, and for acetic acid, it's 4.76. The weakest acid has the highest pKa. So the highest pKa is the one that is less willing to give away its proton, so that's going to be acetone. So I'll rank that as 1. The next one is phenol, which is 2, and then the 2,4-pentane-dione, 3, and then our most acidic is acetic acid. So the pKa values are related to logarithms and equilibrium constants. So we can use this to predict whether a reaction is going to happen. We're going to compare acids. And equilibrium will favor the one with the higher pKa. So acetic acid, we said, was around 4.76. And that's our acid versus the hydroxide ion, which is negatively charged. On the reverse side, the acetate ion is going to be the one accepting the protons. So here's my conjugate base. This is my conjugate acid. So if I'm comparing the acids on both sides, the pKa of water is 15.74. And equilibrium favors the side with the higher pKa, which is 15.74. So that's going to be this side. So this reaction will form. So if you have a higher pKa, water is less likely to give up its proton to shift it back into the reactant side. So our equilibrium is going to favor water because that's going to have more water in solution versus the acetic acid and hydroxide ion. So if we look at these, our pKa's are given to us. We can decide based on just the pKa which is going to happen. If I'm looking at acetylene, which has a pKa of 25 versus water, which has the pKa of 15.74, our equilibrium is going to favor the side with the higher pKa. That will be the reactants in this situation. And then in the next reaction, I have acetone versus sodium amide. We have a pKa of 19 versus the pKa of 36. There is the favored side over here. Next, we'll look at some organic acids. Organic acids are characterized by having positively polarized hydrogen atoms, or those that lose a proton from OH, such as methanol and acetic acid. So here we're losing these protons. In acetone, this is losing a proton from CH because it's next to a carbonyl. That makes it more acidic. So methanol has a pKa of 15.5, which is very similar to water. For acetic acid, we've seen now that's 4.76. And for acetone, the hydrogen next to the carbonyl is 19.3. So it's less acidic than water. These organic acids can form sometimes because the anion that forms can be stabilized by a highly electronegative atom. So hydrogen, if that donates the proton and acts as the acid, the negative charge is stabilized by the oxygen. And that is okay because oxygen is electronegative. So oxygen can handle that negative charge. In the next organic acid here, this is the acetic acid. Once the carboxylic acid loses that proton, we form this carboxylate, which can be resonance stabilized. So these electrons can form here, form a bond there. Or this negative charge here is stabilized by resonance. So this is the acid that had the pKa of around 4.76. This methanol has the pKa of 15.5. That one is a weaker acid because it has oxygen being negative to stabilize, which is okay. But if we can introduce resonance stabilization, now that negative charge can be spread over 3 atoms instead of just the one in oxygen. So that's why the pKa of acetic acid is 4.76, is because we have that stabilization over the 3 atoms. In acetone, that pKa was around 19. So here we have some resonance stabilization as well. There's resonance stabilization here, but it's not as strong as with the acetate ion because we're stabilizing between a carbon, carbon, and oxygen versus the oxygen, carbon, and oxygen. So oxygen's better at holding the negative charge, which is why the acetate is going to be a stronger acid. This one again is also resonance stabilized, but it's to a lesser extent than the C double bond O on either side. And there's our hybrid carbonyl acetate ion. Acetone is going to be less resonance stabilized than the other one because of the atoms involved. So when we're looking at organic bases, these tend to be nitrogens or oxygens with lone pair electrons. The conjugate base of any acid with a pKa that's greater than water will deprotonate water. Some conjugate base that has a pKa that's going to be greater than water will deprotonate water. So methanol has a pKa of 16. So that means that the CH3O- is going to deprotonate water. So the conjugate base of that acid is going to deprotonate water. So organic bases generally have an atom with a lone pair of electrons that can bond to a proton. And these atoms are usually nitrogen or oxygen. The nitrogen-containing compounds usually come from ammonia, and oxygen-containing compounds can react as bases with a strong acid or as acids with a strong base. We've seen water act as an acid or a base, and methanol can do the same thing. A Lewis acid is an electron pair acceptor. And then a Lewis base is an electron pair donor. So it's not exactly the same as a Bronsted acid because Bronsted acids cannot directly accept an electron pair, only the proton. Lewis acids are not ranked in a scale of strong acid or strong base like Bronsted's are, so there's no pKa's for Lewis acids. But a Lewis base usually is the lone pair that can donate its electrons, so this would be a Lewis base. So oftentimes a nitrogen or an oxygen can act as a Lewis base, and something with a vacant orbital or an empty orbital is a Lewis acid. So B can donate its electrons to A, and then this is the electron pair that's donated to form a new bond there. A lot of times these Lewis acids are going to be metals, in the case of boron trifluoride here. So this is a Lewis acid. And boron is accepting a pair of electrons from the oxygen here, which is acting as our Lewis base. And then we create an acid-base complex. Lewis bases can accept protons as well as Lewis acids. So this definition is kind of the same for a Bronsted base. So a Lewis base can accept electrons or protons. So in the top equation there, we have kind of the definition of a Bronsted acid base, where HCl is the acid donating the proton and oxygen is the base. Most oxygen and nitrogen containing organic compounds are Lewis bases because they have lone pairs of electrons. Some compounds can act as either. We have a list of some Lewis bases. Alcohols, ethers, aldehydes, ketones, these can all act as Lewis bases, as can different carboxylic acid derivatives. So here, using the curved arrows, show how the species can act as a Lewis base in their reactions with HCl. So HCl is going to be acting as our Lewis acid, and the lone pair of electrons on oxygen is going to be the Lewis base. It's going to give its electrons to hydrogen, and we form an acid-base complex. And with dimethylamine, the HCl is acting as our Lewis acid. The lone pair electrons on nitrogen are acting as the Lewis base, donating the electrons. And then there's the acid-base complex. We can also have non-covalent interactions between molecules, and these are intermolecular forces that are present in proteins and nucleic acids. So we're going to see this in our different biological molecules. We have dipole-dipole interactions, and that is shown in A. In a dipole-dipole, we have positive and negative poles, kind of like magnets. So we have the positive and negative that are attracted to each other, and they can line themselves up. B illustrates dispersion forces, where the only relationship they have to each other is being near one another. This space-filling model here is another representation of a dipole-dipole. There's a positive N on one side and a negative on the other. Another type of non-covalent interaction is hydrogen bonds. In hydrogen bonds, these are strong dipole-dipole bonds that happen between OH and NH. We're not going to see a hydrogen bond between a C and an H, only between OHs and NHs. One of the strongest places that we see hydrogen bonds is in water. So those dotted lines there are representing hydrogen bonding that occur between oxygen and hydrogen. They're very attracted to each other. Oxygen's very electronegative, hydrogen is not, and they have this interaction that can help their intermolecular properties. We can also see a hydrogen bond between nitrogen and hydrogen here. These hydrogen bonds cause water to have higher boiling points, and also other compounds that have hydrogen bonding interactions. We also see hydrogen bonds in enzymes, which holds enzymes together. These hydrogen bonds also cause our strands of DNA to pair up and then coil to form the helix. And with that, we also see on our right here, there's a strand of DNA, and it forms this ladder here. There's hydrogen bonds in between each of these that we can't see. Something that is hydrophilic is water-loving. Which are hydrogen bonds, and hydrophobic things are water-fearing. So here's a little something extra from cocaine to dental anesthetics. Alkaloids come from plants. These are amines that come from natural sources. There are over 20,000 known, and many of them have biological properties. Half of pharmaceutical drugs are derivatives of these alkaloids. So we have anesthetics, which include Procaine or Novocaine, which is used at the dentist. We have lidocaine and mepivacaine. These are fast-acting anesthetics that will last about 3 to 6 hours. And then we also have the two below there, which I'm not going to try to pronounce. Those are fast-acting, but they fade after about 45 minutes. So those would not be used for long surgeries. There's structures of cocaine, ephedrine, and morphine over on the right side of your slide. Cocaine used to be in the beverage Coca-Cola, but it was removed in 1906 when they discovered the effects of that. So we're going to see some of these. So these are compounds that are capable of hydrogen bonding and also dipole-dipole interactions.